Here I have a loop-the-loop and a cart that is suited to this particular track. And I want to illustrate conservation of momentum here, except with a little bit of a twist. If I start this cart out at some height right here, I would expect that it will end up over here at 0 speed at the same height. But what if I want to make it go all the way around the loop-the-loop? How high do I have to release it? The answer may surprise you. If I go to the same height here and I release it, guess what's going to happen? It's not going to be able to complete the circle because it doesn't have enough centripetal motion. So here I go, I'm going to release it, and sure enough it fails. In fact, what I need in order to make it all the way up to the top is that I need the centripetal force to at least equal the gravitational force. At the top here, if I think about the forces acting on the cart, there'll be weight pulling down. There'll also be a normal force due to the track. Which way does that point? Well, if there's no track here, this thing might go off the track like this, so it must be pushing inward. I want to get to the point, the slipping point, where just as it gets to this point here, it loses contact with the track. That would mean n equal to 0. So in other words, the centripetal force, F equals mv squared over r, has to at least equal the weight mg. It turns out, if this is the radius of this circle right here, it turns out that I need not just twice the radius, I need, I believe, 5.5 radii. So let me release it from the top, and this is going to be very close, so let's see whether or not it makes it around. And you'll give me a couple of opportunities to do this in case the first one crashes. Okay, here goes. Well, it spun out at the bottom there, but it did make it all the way around the circle. It just had trouble staying on the track.